Ever really thought about your evening cup of decaf? How do they get the caffeine out but leave that rich coffee taste in? Well, it turns out the secret isn't a chemical trick, it's a map. A secret map for matter called a phase diagram.
All right, so let's start with what I like to call the coffee conundrum. We love coffee, right? But sometimes, especially later in the day, that caffeine kick is just not what you need. So how in the world do you get rid of it without totally wrecking the taste?
I mean, really stop and think about this for a second. A single coffee bean has over 400 different chemical compounds that create that incredible aroma and flavor we love. The challenge is almost surgical. You have to remove just one of those molecules, caffeine, and leave all that other good stuff perfectly untouched. So the first attempts, yeah, they were a bit clumsy. You could just wash the beans with hot water. And sure, caffeine dissolves in water, but so do a ton of those precious flavor compounds. So you got decaf, but it was kind of bland. Other methods used chemical solvents, which were definitely better at targeting the caffeine, but they could still strip away some flavor, and, people weren't thrilled about potential chemical residue. The mission was always clear. Get the caffeine out, keep the taste in. So how did they finally crack the code? Well, they turned to this incredibly powerful scientific tool. It's a special kind of map that can tell us exactly how any substance is going to behave under different conditions. And this map is called a phase diagram. So what is this thing, a phase diagram? It's basically a cheat sheet for any substance in the universe. It's a graph that maps out what state it's going to be in, solid, liquid, or gas, depending on two simple things, its temperature and the pressure it's under. Probably the easiest way to get your head around this is to think of it like a weather map, but instead of predicting rain or sun, it predicts the state of matter. You just find the temperature on the bottom axis, the pressure on the side axis, and see where they meet on the chart. And boom, the map tells you if you're looking at a solid, a liquid, or a gas. To really get good at reading this kind of map, let's practice on a substance we all know inside and out, good old H2O, water. If we can figure out the rules on water's map, we can pretty much unlock the secrets of anything else. Okay, you see all those lines that divide the map into different regions? Those are the most important part. They're called phase boundaries. Think of them like borders. Anytime you cross one of those lines by changing the temperature or pressure, the substance has to change its state. It's like ice melting into water, or water boiling into steam. So let's trace them together. This curve right here, between solid and liquid, that's the line for melting and freezing. And this one, separating liquid and gas, that's your boiling point line. And then there's this interesting one down here, between solid and gas. That's for something called sublimation. That's when a solid, like ice, turns directly into a gas without ever being a liquid. And here's where water gets a little weird, in a really cool way. If you look closely, that line between solid and liquid is tilted slightly to the left. That's a huge deal. It means that if you squeeze ice really, really hard, increase the pressure, it actually melts at a lower temperature. This is a big part of why massive glaciers can move. Their own weight creates so much pressure at the bottom that it melts a super thin layer of ice, creating a liquid lubricant for the whole thing to slide. And what about that solid to gas line, sublimation? Well, that's the secret behind freeze drying. You take frozen food, stick it in a vacuum chamber to drop the pressure way, way down, and the ice just turns directly into water vapor. It gets sucked away, leaving the food structure perfectly preserved. And yep, this is exactly how they make astronaut ice cream. Now, check this out. See this one little spot on the map where all three lines crash into each other? That's called the triple point. It is the one specific, unique combination of temperature and pressure where a substance can exist as a solid, a liquid, and a gas, all at the exact same time, in perfect balance. It's a critical landmark on our map. Okay, map reading skills unlocked. Now let's get back to our coffee problem. To solve this puzzle, we're going to swap out the map for water and bring in the map for another substance we all know, carbon dioxide, CO2. And when you put their maps side by side, whoa, you can see just how different they are. Look where CO2's triple point is. It's way above our normal atmospheric pressure. That's the reason you never see liquid carbon dioxide just sitting around. At the pressures we live in, solid CO2 or dry ice goes straight from a solid to a gas. It sublimates. But if you follow the map for CO2 way, way up into really high temperatures and really high pressures, something wild happens. That line separating the liquid and gas phases, it just ends. It stops. And up here, in this strange, uncharted territory, matter enters a fourth state.
it becomes a supercritical fluid.
And this supercritical fluid is the hero of our story. It's amazing. It gets the best powers from both worlds. It has a density like a liquid, which means it's great at dissolving things. But it flows like a gas, with almost no resistance, so it can seep into the tiniest, most microscopic pores of a coffee bean. And the best part? For CO2, it's completely non-toxic and safe. So here it is, the whole elegant solution. First, they take the green coffee beans and steam them a bit to open up their pores. Then they go into a big, high-pressure tank. You pump in carbon dioxide, and you just follow the map. You raise the temperature and pressure past that critical point. The CO2 turns into our magical, supercritical fluid. It flows like a gas deep inside the beans and acts like a liquid solvent, perfectly dissolving and pulling out 97 to 99% of the caffeine, while leaving the bigger, more complex flavor molecules behind. Then you just release the pressure. The CO2 instantly turns back into a harmless gas and just evaporates. And what's left behind? Pure, delicious, and perfectly decaffeinated coffee beans. It's just brilliant. So you see, this incredibly clever solution is really a testament to the power of these maps. And as you can probably guess, their usefulness goes way, way beyond just making a better cup of decaf.
So what's the big takeaway here? We've seen that these phase diagrams aren't just for chemistry class. They actually explain real-world things, from how glaciers move to how astronaut ice cream is made. And by understanding them, we've unlocked this amazing power of supercritical fluids, a technology so precise that it's also used to extract delicate flavor oils from citrus peels, or even to make healthier snacks by pulling the fat right out of potato chips. And that really leads to a final thought. We now have this incredible molecular toolkit, almost like a molecular scalpel, that lets us be incredibly selective to pull one specific thread out of a complex fabric without unraveling the whole thing. It just makes you wonder, what other huge problems in medicine or manufacturing or even environmental cleanup could we solve with it next?